Presentation of Science Trek on Idaho Public Television is made possible through the generous support of the Laura Moore Cunningham Foundation, committed to fulfilling the Moore family legacy of building the great state of Idaho.
A simple machine has few or no moving parts. But because of simple machines, humans have been able to create the wonders of the world. Combine simple machines and you can create almost anything that makes work easier. Find out more about simple machines. Science Trek is next. Hi, I'm Joan Cartan Hansen. Welcome to Science Trek and welcome to the Discovery Center of Idaho. We're here today to answer your questions about simple machines. But before we do, let's learn a little bit more. Simple machines help us make better use of our muscles to do a thing called work. Don't be fooled by their name. Simple machines help create things that are very complex. A simple machine controls the direction of the force or energy we apply. They're very handy because they make many movements and jobs easier to do. Simple machines work either alone or in various combinations. They make up most of the gadgets and mechanical devices we use every day. The 6 simple machines are the lever, the pulley, the wheel and axle, the inclined plane, the wedge, and the screw. The lever is the oldest simple machine. It's probably best described with a seesaw. Every lever, every seesaw, has a fulcrum. That's the point where the seesaw moves. It's right in the middle. The way a lever works is downward motion on one end results in upward motion at the other. Scissors are also a good example of a lever. Next are pulleys. There are pulleys in cranes and elevators, and your fishing pole has a pulley too. A pulley helps you move something up or down. It's a special wheel with a rope around it. When you give the rope a tug, the object at the other end can easily be lifted. If you combine several pulleys, you can lift something that normally you'd never be able to carry. The wheel and axle is best described with a good look at the tires of a car or truck. A wheel and axle rotate together. The wheel is locked to a central axle. When one turns, they both turn. The wheel and axle allows you to move the heavy car or truck. Another wheel and axle is a knob on a radio. The most simple of the simple machines is the inclined plane. It's a sloping surface used to lift or help move heavy loads with little effort. A wheelchair ramp is a good example of an inclined plane. It allows someone to go inside without trudging up the stairs. With an inclined plane, even though you're going a longer distance, it takes less effort to move. Next is the wedge. It's shaped a little like an inclined plane. Have you ever seen someone chop wood? They're probably using a wedge between the axe and the log to help drive a force into the wood and split it apart. Another simple machine is the screw. Anytime you take the lid off a jar of peanut butter, you're using it. A screw is a long incline with a central core and a groove wrapped around it. Every time you screw off the lid from a jar, you're seeing a simple machine in action. Screws are also very useful to hold things together. It's hard not to find examples of simple machines. They've been around for thousands of years. Humans use simple machines to build the Great Pyramids. We use them every day, in cars, schoolrooms, everywhere. The bottom line is that simple machines are tools to make work easier. And joining me now to answer your questions about simple machines are John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and Catherine Devine, Assistant Professor of Physics at the College of Idaho. Okay, let's go to your questions.
Hi, my name's Magenta, and I go to Garfield Elementary. And my question is, why are they called simple machines?
Most of our machines that we work with every day are very complicated, but we find if we really look at them, they're all built up of just a few simple building blocks. And those 6 simple machines that you've been studying in class are those building blocks. And pretty much everything we have are some combinations of those. So it's what we ended up calling them.
Hi, my name is Lavita, and I go to Basin Elementary School, and my question is, who made the first simple machine?
I'm not sure anybody actually knows who made the first simple machine, but I know that they've found evidence of some of the machines, like wheels and axles, that go back at least 5,000 years ago, and wedges that date back far longer than that. So I'm not sure there's a really well-known answer to that, but thousands and thousands of years ago, people were using these simple machines.
And I think it's also important to realize that when these machines were being developed, all the cultures didn't speak to each other. We didn't have the internet. We didn't have any kind of communication. They didn't even know of each other's existence. And many of the machines were developed totally independently by many different cultures and many different people. So there really isn't just one answer to that question.
Hi, my name is Natalie. I go to Garfield Elementary. My question is, how is work measured?
Well, we'll start with the units, which are units of energy. And so energy, to kind of put energy in perspective, because that kind of gives the question, how is energy measured? Physicists use units called joules, and those are measures of how much energy it takes to do work. And you can use that to measure the amount of energy, like in the food you eat. Another measure of energy similar to a joule that you might know at home is a calorie. So those units of energy are how work is also quantified, and so work is measured in units of joules. But for how an instrument might measure work, for example, like a scale measures weight, that's a little trickier. There's different types of work, and there's different types of instruments to measure that. Depends on what kind of work you're doing, whether it's the work of lifting something against gravity or the work done against friction. So when it comes to the tool you would use to measure work, that completely depends on the type of work that you're trying to measure.
And if I could add on that a little bit, if you wanted to think of it in its simplest terms, physical work, like the work people do, it's force through a distance. So if you push a block across the floor and you had to put a force on there to do it, it's the force times the distance. And one of the concepts about work that's important to understand is that it's a combination of two different physical things. Force and distance in this case, volts and current, volts and amps if it's electrical, and so on. So in any time you're talking about work or energy, it's really two different things considered together.
Drew would like to know, what is the most useful simple machine?
That's a very difficult question to answer, because if the purpose that you're trying to use, that you're trying to apply a machine to, if that purpose needs a lever, that's the machine you need. If it's a wedge, then that's the most useful machine. Probably the most common machine is the wheel, at least in modern day, because it's so tied up with transportation and all the automation and mechanism of our society. But they're all very, very useful, and I don't think I'd say one is more important than the others.
Hi, my name is Shelby, and I go to Kamiah Elementary School in Kamiah, Idaho. My question is, how do you make a simple machine?
There's a lot of different ways to do that, but I think the easiest simple machine to make is the lever. So you have a long, rigid bar and a rock or some fixed object to lean it against, and then you can pivot around that one object. Wheels are harder to make because they've got to be perfectly round, or they're not very good machines. Another very easy machine to make, if you want to do, is a wedge. So any small block of wood or metal that tapers to a point can be used as a wedge, and you could use it to maybe get under a heavy weight, and it can start moving it up and things like that.
Audrey asks, how big can a simple machine get?
As big as you wanted it to be. I think the sky's the limit when it comes to making a machine bigger. I think some of the limits would be being able to afford the material that it would take to make your machine huge. And so the reason we don't make really big machines is because they're expensive, and at some point it's big enough to do the job you need it to do. And so you don't need a pulley and a crane to be any bigger than it needs to be to lift stuff up to the top floor, for example. I think what can be a little bit more challenging actually for machine makers is trying to make them as small as they can be. So for example, in a watch, you have these fine, tiny wheels and tiny levers. And so some of the challenge in machine building isn't actually making a very large machine, it's making very tiny machines.
We've moved over to another part of the Discovery Center, and joining me is Woody Sobey. You're going to show us some simple machines experiments.
Exactly. We're going to get started with the lever, a very fun one. And what we have here is a balancing beam which acts as a lever. We have the fulcrum, the pivot point right there in the middle. And what we're going to do is we're going to start with a simple experiment. I'm going to take this one weight and I'm place it right here on the 5th peg out. And I'm going to ask you to take one peg and see if you can place it on your side to balance it out. Excellent. So by placing that one on the 5th peg, we can see that both sides are now balanced. There's the same forces pushing down on both sides. Now what I'm going to do is I'm going to change it around a little bit, and I'm going to take a second weight, and I'm going to place this on the same peg on my side, but you don't have a second peg. So how do you balance this with only one weight?
Okay. Well, I think it involves math, but I think if I do this, it should balance.
Excellent. It certainly does involve math, and we've got it balanced there. So we have 2 weights at 5, and we have 1 weight at 10. So those 2 are going to be the same force pushing down on both sides of our lever. So what we can see here is you can have a small force pushing down further away equals a large force pushing down closer in, and that's really the power of levers. So now what we're going to do is we're going to try using that same idea of the levers again, this time on a larger lever, and we're going to try to use that concept of small forces further out lifting larger forces. And what we're going to do is we're going to try and lift Hannah off the ground. So we have our volunteer Hannah here.
Thank you for joining us.
And we're going to go ahead and have her stand on the edge of the beam right there. Excellent. And when you're standing on that, I'm going to try to push down here. And by pushing down on it, I can't lift you because the force is too much. I'd have to put all my weight on it. But what we're going to have you do is step back. And now we're going to move the pivot point, the fulcrum here. We're going to slide it out further. And this time, we'll have you go ahead and stand on that again. And now, because we have the difference in length, we're going to have a small force over here lifting you right up off the ground.
Voila! We're going to move on to our next simple machine. It's the pulley. Tell us about it.
Excellent. And so the pulley allows you to redirect forces, but it also allows you to multiply forces by using multiple pulleys together. So what we have is the first one is just a single pulley, and by pulling on this, you can lift the bowling ball, but you have to lift the entire weight of the bowling ball, and you get no mechanical advantage. From here, we can move on to 2 pulleys, which will give us some mechanical advantage. So move this over. And now when we pull on this rope, we're going to be getting the mechanical advantage, so it'll be easier to pull, but we'll have to pull it much further in order to lift the bowling ball the same distance. Then what we can do is we can try going over to our final pulley, which actually has 4 pulleys on it and is much easier to lift, but as a result, you have to pull the pulleys much, much farther. So with this one, you can start up and you just keep pulling and pulling and pulling before you get the bowling ball all the way to the top.
So it takes less force when you have more pulleys, so it makes the work easier.
It makes it much easier, but you have to do it over a much longer distance.
You know, I have a friend, George, who's going on a trip, but he's too heavy for me to move. Can you help me?
Well, I think we could certainly use some of these pulleys to help out. Which one do you want to try?
Let's try the 4-pulley system.
Seems like a good idea. Let's see if it works.
There we go.
All right.
And I'm using another simple machine, the wheel and axle, to help move George out of here. Thank you so much for your demonstrations.
Certainly. I'm glad you could make it.
Okay, let's go back to your questions.
Hi, my name is Ashton. I'm from Basin Elementary. My question is, how does a lever work?
Energy or work is a force through a distance, and a lever gives you a way of exerting force at another location. So you push a lever at one end, it exerts force on the other. But because of where the fulcrum is, or the pivot, the amount of distance you travel will be different. So if you have a lever set up so that you can exert a force of, say, 1 unit or 1 pound or 1 newton through 1 meter, the fulcrum can make a larger force at the other location, but it would be less distance. There's a trade-off between you can multiply force. The force can get bigger, but the distance will get smaller, and the other way around. If the distance gets bigger, the force will get smaller.
Isabella asks, when my teacher pulls her map down, what simple machine is she using?
I think she's probably using the wheel and axle primarily. So when your map is on a round tube, and when you pull on the string, it wraps down. And so what it's wrapping around is a long wheel, basically, or two wheels on the end. And then those wheels are on a spring mechanism so that when you can give it a sharp yank, it'll wrap back up again.
And if I could just add to that, if you were to go in there and take it apart and look at all the different things going on there, and you probably shouldn't do this, but if you could do this,
The teacher might get upset.
you'd probably find lots of other simple machines. There's probably little levers in there they're the things that lock it in place, so that's why it doesn't go flying back up again when you bring it back down. So there's any one of these machines, any common object we have these days, you'll probably find several machines within them.
Hi, my name is Sam. I am from Basin Elementary School, and my question is, who made the pulley?
That's a difficult question to answer, but we know some of the answer. Archimedes in the 3rd century BC was the oldest record of the pulley. So he is credited as inventing the pulley, but it gets us into a more interesting discussion. Is the pulley might have been around for a long time before that, and in many other cultures, but he was the first one to write it down in a way that survived to modern times. So he's credited it just because he's the oldest record of it, but it might have happened in other places at other times as well.
Hi, my name is Ben. I go to Garfield Elementary, and my question is, do only some simple machines only come from some cultures?
Well, I think like the wheel and the wedge and the lever, those got developed independently across many different cultures thousands of years ago, just because they are fairly simple to build and kind of invent. As for things like the screw and the pulley, I'm not actually sure who invented those, but those would be a little bit trickier and require a little bit more ingenuity. So, but for the very, very simple machines like wedges, levers, wheels, I think those were independently developed in many different cultures.
My name is Mustafa. I go to Garfield Elementary. How do we define a tool?
Well, I think, I'm not sure there's a really solid definition of that, but I would consider a tool as something that we as humans made. We took something and fabricated it in some way, and then we use that to manipulate our environment in some way. So if you just pick up a stick and hit something with it, that probably wouldn't be considered a tool. But if you took up a stick and broke it off to the right length and broke off all the little branches on it and used it to, say, hit a baseball, that would probably count as a tool.
Siobhan asks, what is the most weight a pulley can lift?
I don't think there's actually any limit on how much weight a pulley can lift. You can design, as long as you design your pulley correctly. And so some of the things you'd have to think about to make a very strong pulley would be the tension that the rope in the pulley system can hold. And so you need to make a very strong rope. So for example, in an elevator cable or a tram car, something that's running large, carrying people, those are made of large steel cables. And so those are very strong pulleys or rope systems. And so if you made your cable or rope strong enough and you made your pulley large enough, you could lift however much weight you needed. I think the reason that we don't have pulleys that can lift the weight of the planet or whatever is just because you have to design your machine for the purpose that you need. And so depending on how much weight you need to lift with your pulley, that would kind of put the limit on how big or strong your pulley would have to be.
My name is Darwin, and I go to Garfield Elementary. And my question is, are there any new simple machines since the original 6 were named?
I don't think so. I mean, this categorization of the simple machines goes back hundreds of years, and we've developed countless machines since then, but they're all combinations of those same 6. So there's no new ones, but we'd be interested in hearing if you had any ideas.
Simple machines make it easier to do things like move large objects, but you're actually doing the same amount of work. Simple machines redirect or change the size of the force you need to do something, so it's a trade-off of energy when using simple machines.
My name's Emilio, and I go to Garfield Elementary. My question is, what is your favorite simple machine and why?
Well, what's your machine? What's your favorite machine?
It's tough to narrow them down. I've been thinking about this. So I think I like pulleys a lot. Anyone who's gone camping and had to hang food away from a hungry bear, pulleys are very good for hanging bear ropes. So that puts pulleys up in the top. I like my bike a lot. So wheels and axles and levers. My bike would not be rideable without those. So it's kind of a toss-up between those three. And then, ramps are really nice. I'm not super strong, so when I have to lift up anything into my house, I usually use it up a ramp on wheels rather than trying to just lift it. So I can't narrow it down. How about you?
I would agree. It's hard to imagine anything we do on a daily basis without all of 6 of the machines. I think wheels are probably the most common one because they're so central to transportation for how we get around, whether it's your bicycle or your car or your skateboard or your scooter. But for some reason, I'm not sure why, I'm kind of partial to pulleys. I think pulleys, very simple little, they're kinds of wheels with rope, and you can just make amazing things. Elevators require pulleys, things like that. So.
Joe asks, how do we use wedges?
Well, I use wedges when I split wood. That's probably the most common use I have of a wedge. And so what a wedge does is it's used to either lift so you put the wedge underneath something and it separates it off the floor. It might separate 2 parts away from each other. So in splitting wood, you put the wedge into your big block, hit it, and it pushes the pieces of wood apart. So you get 2 smaller pieces of wood that'll fit in your fireplace. Other examples of wedges are if you have something heavy on the floor and you need to kind of get it off the floor or break the seal with the floor or whatever, then you can put the wedge underneath it and it'll push it up. John, how do you use wedges?
Well, I think probably the most common wedge that I've seen around, it's probably one in your classroom. It's a doorstop. So a wedge that if you want to keep the door open, it's the triangular shaped piece of wood or rubber or plastic that you shove under the bottom of the door, and it's the friction against the floor and against the door that keeps it there. And it's not so much friction that you can't pop it out later when you want to close the door, but it's what keeps it there. So that's a real common application of a wedge.
Sawyer would like to know, how do screws connect to walls?
The screws are actually pretty interesting. If you take one out of a toolbox and look at it, what you'll see is that the thing that wraps around it. So you've got something that looks like a nail with a metal piece that wraps around it. And so that thing that wraps around it, if you look very carefully, is actually just an inclined plane, which is another one of your simple machines. So you've got your ramp, but it's a ramp being wrapped around the screw. And so imagine now if you take your screw and you twist it into the wall, what it's doing is it's actually pulling the wall up the inclined plane, and your screw goes into the wall and holds steady. So it's kind of a simple machine made out of another simple machine.
Parker asks, how do simple machines help people?
Simple machines help people in countless ways every day. In fact, that's why simple machines came into being, because people in the ancient cultures needed to do something better, needed to do something easier, needed to multiply their force or their effort. And they used that to help, whether it was to move a rock that could be used to build a home, or to move large stones to make the pyramids, to commemorate the pharaohs. There's just countless ways that happens every single day. And I would encourage you to actually look around as you go through your day and find those simple machines and think about that.
Every time you ride your bike to school, you're using simple machines. Every time you prop a door open with a doorstop, you're using a simple machine. So I agree. You should just look around during the day, and I think you'll notice that almost every moment of the day you're being helped out by a simple machine in some way.
Roman would like to know, how do machines get built?
How do machines get built? Well, simple machines are one of the reasons they are simple is they've been around for a long time, and they were built without a lot of tools, without a lot of technology. But in the modern world, machines can be very complicated. They're made up of many combinations of the simple machines and compounding them together. And so they're built by engineers who try to understand what the machine, what the desire, what the need for the machine is, like an automobile, and they design it. They understand their lessons from physics and from the other classes they've taken, and figure out how big the parts have to be and how they fit together and what materials they're made out of and how you manufacture them and how you put them together in a way to make it work. It's a very complicated process.
Catherine, before we run out of time, let me ask why you decided to become a scientist.
I think it was just something that I always really enjoyed in school. I've always really liked doing hands-on sort of things. And so science was a way to test predictions and challenge myself, but in a fun, hands-on way. I also really like to understand the world around me. And so when I went into college, I started studying physics specifically because I really like math, and I like that physics is a science that uses math to explain pretty much everything. And so I really get a kick out of that, and I really enjoy doing it. So that's why I started studying it. The reason I stayed with it is because then I discovered I really like teaching too. And so my job lets me not only do science, but also teach science. So it's kind of a dream job that way.
And John, if someone is interested in becoming a scientist, what should he or she study in school?
I think probably the most important thing is obviously science, because that's the basic topic that scientists work with every day, and a very important part of that as well is mathematics. All the different aspects of mathematics feed into and become part of science as well.
I think one other thing, just to add to that a lot of schools are starting to offer is anything to do with computers too. I think students, if when you get later on in school the opportunity to learn any sort of computer programming or computer skills, I think that's becoming more and more important for scientists these days, and more of a need for students coming in and to study in college is being able to understand how computers work and also how to do a little bit of programming. So if that's available, that's a really good thing to learn as well.
And I think it's also important to realize that the other topics, the other subjects you study are important too. If you're a very good scientist and you do science well and you understand math real well, but you can't communicate it to anyone, you're wasting your time. So your ability to write and to speak and to interact with people, these are very important. And I think also what you find is the best scientists, the most accomplished scientists, are very creative people. And so studying the arts and studying creative processes like music and science go together very often in a lot of people's careers. These are things that really, really build on each other.
I'm sorry, but we've run out of time. My thanks to John and Catherine for answering students' questions.
Thank you so much for having us.
It's great to be here.
And thanks to the folks here at the Discovery Center of Idaho for hosting us. You can learn more about simple machines and lots of other scientific topics on the Science Trek website. We'll answer more questions about simple machines on Science Trek, the web show. And if you want to submit a question for Science Trek, it's easy, and you and your class can win prizes. You can send it as an email or a video question. Record it on your webcam or cell phone, and if you're an educator, we'll even lend you a camera. Our last prize winner was Quinn in Jamie Miller's class at Caldwell Adventist Elementary School. So to find out all about simple machines, how to send in your questions, and how to win, go to the Science Trek website. And each week, check out my blog for the latest science news for kids. You'll find it all at idahoptv.org/Science Trek. Thanks for joining us. We'll see you next time on Science Trek.
Presentation of Science Trek on Idaho Public Television is made possible through the generous support of the Laura Moore Cunningham Foundation, committed to fulfilling the Moore family legacy of building the great state of Idaho.
If you want to learn more about this topic or watch our videos, check out the Science Trek website at idahoptv.org/Science Trek.